I want you to assume in this particular question that net force equals, that the coefficient of friction equals 0. This block is 5m. This block is m. Let's assume the pulley for the time being is massless. And let's say that the box is distance h above the ground. I'd like to know the acceleration of this system. And in addition to that, I'd like to know how fast the box is going when it hits the ground. We've done this a lot. Prove that you remember something, anything. I'm likely to get over it, but maybe not. Is it a first law problem or a second law problem? Good chance. Probably because I asked what is the acceleration of the system. That's a big clue that it's probably a second law problem. So net force equals ma. I don't really want to go about the whole thing, but I'm going to. The mass on the table. Let's talk about the forces acting on it. I'm going to go through my list of forces, starting with a fundamental force. Is there a fundamental force acting on it? Sure, gravity, downwards. How big? 5 mg. Is it in contact with the surface? Then yes, there's a normal force acting on it, upwards. Does it have any strings attached to it? Yes. Then they're likely pulling in the direction of the string. Those appear to be the forces acting on this block. Based on the fact we're using Newton's law, Newton's second law, I'm not even going to worry about the net force in the y direction. That's 0. I don't care about that because there's no friction and I don't need the normal force. Look, I did not ask a hard one that would have required normal force to be used here. But I will say that tension equals 5 ma. Net force, T, equals the mass of the object, 5m, times its acceleration, a. However, there's another object here. Is it experiencing any forces? Sure. What's one? Gravity, downwards, mg. Is it in contact with the surface? No. Does it have a string attached to it? Yes. Upward force, tension, drawn specifically less than mg, because I know that it has to be less or it can't accelerate. It should be an unbalanced force. So when I draw my picture, I should make sure that the tension upwards looks smaller than the weight downwards. And I should have endeavored to make this arrow and this arrow the same size. But I digress. So net force equals ma. I will remember that I should make one common direction, the common direction I call positive. So I will make downwards positive for this object, where mg minus t equals ma. Well, all that Newton's laws can do is produce a relationship, and I have produced 2 of them. And if I recall, I could find a way to remove tension by adding these 2 equations together or using substitution, and I will get mg equals m plus 5m times a. Not a surprise, because net force equals mass of a system times a. The net force is the mass that we hung. The whole system is moving, so it's the sum of all the masses times a. We probably didn't have to do all this. We could have probably just put mg as the weight that's hung, 6m is the total mass of the system, and a is the acceleration. Either way, you solve this for a, and you get 1/6 g. So my snarkiness is warranted, right? Okay. Let's just rub a little more insult in there, shall we? Does the box on the table change its height? So it doesn't really have any potential energy to deal with in this problem because its height never changes. Does the box that's hanging change its height? I think so. It starts at h above the ground. Eventually it's going to be how close to the ground? Well, 0, right? We want to find out how fast it's going when it's at 0. So I'm going to say at the start of this problem, we have gravitational potential energy, only from the one box though, because the other box's height never changes. After a few moments, this box will reach the ground and this box will have moved to the side. But at this moment, this box will be moving and this box will be moving, correct? Which of those 2 boxes has kinetic energy? The one that's moving. Which one's moving? Both of them. They're both moving, right? I'm not trying to be a jerk, but both of them are moving. Because I saw this on some of your papers, but this energy caused the box that's hanging to move, and it caused the box on the table to move. Right? Nothing surprising here. We've seen this before. Add this together, and I'm going to get 3 mv squared equals mgh. Solve that for h. Oh, I don't want to solve that for h. What am I doing? Solve that for v, and I'll get v equals 1/3 gh, all under the radical. Yep. I could have used kinematics. I probably would have done it over here and said that the initial velocity is 0. We're looking for the final velocity, and my delta x is h. That's probably what I would have done. And that would have been 2 times the acceleration times delta x, 2a delta x equals v squared minus 0 squared. You get the same answer, of course, because 2/6 is 1/3, and then take the square root, so it'll be the same thing. But yeah, you certainly could have done that too. If we were here, this was the inertia of the system, right? The whole system had to be included, because even though it's only this box that's experiencing gravity, these 2 boxes were connected together. So when it came to the system moving, I had to take into account the inertia of the system, because the force was changing the system. Does that make sense? Now, gravity was not acting on both the boxes the same way. Although gravity was acting on this box, there was something to prevent gravity from causing it to accelerate, because the table was counteracting gravity, but only on that box. This box didn't have the table counteracting gravity, so it was unbalanced. That's what caused the system to move. We're going to talk about dynamics. That's what we just did, dynamics. Dynamics are systems in which the net force does not equal 0. All right, we're going to deal with the fact that the net force is unbalanced, and it's going to cause an acceleration. Now, first semester, you probably don't remember, but I spent a whole bunch of time talking about the importance of understanding what this statement means, that it's not an equation. It's a set of instructions, but that it also indicates something to us. And I think a lot of the nuance is lost. In fact, the nuance, this tells us something that may not be obvious, that you have to think about first to understand what it's really trying to communicate. For example, we already know what this is supposed to mean. And here I will reiterate it. It's speeding up or slowing down or changing direction, right? That's it. That's what acceleration is. Going faster, going slower, and or changing the direction you're going. Any of those things constitutes acceleration. But what I really want you to understand is that this is what an object does. Right? Something happens. And again, speeds up or down and or changes direction. Either way, the whole idea is that something changes about your object. This is observable. We can see it happen. If you see something like this happen, you know that something over here was there. You may not be able to see that, but this is what you do to the object. I keep saying object. I can replace it with the word system, but I don't want to make this harder. But you expose it to a force, or maybe a whole bunch of forces. You pull on it, you push on it, you drop it, you throw it across the floor and there's friction acting on it. It's what you do to the object. You may not be able to see this, right? Because there are forces that we can't see, like gravity. You can't see it. But if there's a string on it or if it's touching a surface, you know that it's experiencing a force. But this is something that is done to the object. What's this? What is this? Go ahead. It's mass, the amount of stuff there is. But I would have used a different word in the day that I introduced this. Go ahead.
Inertia.
It's inertia. It's defined as how difficult it is to change the object's motion. An object with more inertia will be more difficult to change. In all these discussions, we've been talking about inertia, because inertia plays a prominent role in how a system behaves. Now, we're about to talk about systems that rotate. They're going to be more complicated. They already are, right? We don't just talk about forces, we talk about torques. And a force, although it's just one thing, a torque is three things: torque arm, size of force, and angle. So torque's already more complicated. If I want to add three torques together, I have to consider 9 things, right? 3 different distances, 3 different forces, and 3 different angles. So I think you can probably imagine there's going to be a law in which there's an unbalanced set of torques. That's the thing you guys are so desperate for, to get the heck out of here. You want to unbalance the torque on the door so you can go, right? Get it to accelerate, rotate, and open. In fact, you're hoping that there will be an observable acceleration. Something will change about the door. It'll go from being at rest to changing its velocity to be open. You're going to fling it open and go busting out of here as fast as possible, probably nailing some poor kid in the head with the door. Brings me happiness when those things happen. You can probably imagine there's going to be something about inertia here, right? Something that has to do with inertia, but like everything else, have you noticed that things seem to be a little bit more complicated when dealing with things that are spinning? So we may have something about inertia here, but it might be more complicated. I would love to say that it'd be something simple like rotational inertia or angular inertia, but it's not. It's called the moment of inertia. It's called the moment of inertia. And we actually use an uppercase I for moment of inertia. So at least it's got I in it for inertia. So Newton's second law for torque would look like this. Now, the reason this is called moment of inertia is because of the nature of what it's trying to tell us. It's the rotational inertia at the moment it's being spun. I'll say that again. We call it moment of inertia because it's the rotational inertia at the moment it's being spun. Think of the meter stick for just a minute. When we were spinning the meter stick about its middle, it had one inertia. And it was clear, I think, for everybody who participated, that there is a different inertia when it was spun about its end. So when we want to decide, well, how much inertia did the meter stick have? It depends. It depends on which axis of rotation you chose. One object can have lots of different moments of inertia because it will depend on how the object is spun. For example, for a meter stick or anything that's long and skinny like this, that has maybe a length L and a mass equal to m, the moment of inertia at its center is 1/12 ml squared, while the moment of inertia at the end is 1/3 ml squared. Same mass, same length, but at the end, it's 4 times greater. than at the middle. It's 4 times harder to spin it at the end than at the middle. Now, keep in mind, right there, that little tiny space, if we tried to spin it about its middle this way, I don't know if you can even see that, but I'm trying. Try to spin it this way, this would also be as if we're spinning it about its middle. But it's no longer L long. It's now whatever this is, say W for width. Which is why, considering a meter stick, that's going to be very small, right? That'll be 1/12 m width squared.